You are welcome once again to another lesson of Physics Paper 2 A-Level at Back Science Education Consultants. I'm Teacher Course and we are proceeding. In the previous lesson, we looked at the capacitance of concentric spheres. You can review, good enough, all the videos are there on YouTube, on our channel, BASC Science Education Consultants. You can find it there and try to follow, and you will get whatever possible you could not have got. Now today we want to look at the capacitance of a parallel plate capacitor. With me is what I've chosen as a model of such a kind. Okay, so if this and this, they are the capacitor plates, this and this are the capacitor plates of that kind of a capacitor. So they are parallel. They are parallel. So between them there is a distance d. Okay, from here to here there is a distance d, and each of them, let's say they are of area A, capital. So we want to see how do we obtain the capacitance of such capacitors. As you can see, it is drawn here. Okay, so each has an area A, and then they are at a separation of distance d meters. So how do we get the capacitance of this? How shall we always obtain that kind of capacitance? How do we get that one? So you can see that due to this potential difference, then there is an electric field intensity which is across. There is that intensity between this upper plate and this lower plate. And what is that electric field intensity? According to Gauss's theorem of electrostatics that we saw in electrostatics, electric field intensity is equaling to sigma out of epsilon naught. We are saying the space here is filled with air, is equal to sigma out of epsilon naught, where this sigma is the surface density of charge, or what we call surface charge density. Therefore, this sigma is the charge per unit area. So if I can substitute this one here, what do I get? I find that I have the electric field intensity equals, where there is this, I substitute this. So that is the charge out of area. Then we had divided by epsilon naught, so it becomes charge out of epsilon naught. Remember, we want the capacitance. We are on electric field intensity. We have also studied from our electrostatics that the electric field intensity is equivalent to the potential gradient, where potential gradient is the potential difference divided by the distance. So for this case, if our potential difference is V and our distance is V meters, therefore our E would be equivalent to this. What does this show us? This actually shows us that charge out of a epsilon naught is equivalent to V out of D. Remember, what is capacitance? That's what we are looking for. What is capacitance? We know that capacitance is the ratio of magnitude of charge to the potential difference. Remember, charge is Q, okay? To the potential difference. So I can see charge here and V there. So how can we get Q out of V? It is as simple as I divide by V both sides and A epsilon naught, and cross multiply this one there. So therefore I can have Q equals A epsilon naught V out of D. But I want to divide by V both sides, so I have the 2 over V. So when I divide by V here and I divide by V there, I remain with 2 out of V equivalent to A epsilon naught out of D. But what is 2 out of V? What is 2 out of V, my friend, there? Yes, we say that 2 out of V is the capacitance. From the definition, where we say that the capacitance is the ratio of magnitude of charge stored on each of the capacitor plates, the magnitude of charge, to the potential difference across them, which is our V. Therefore, that's the capacitance. So I can say that now this is the capacitance. So therefore, I can just say capacitance equals A epsilon naught out of D. That is the capacitance of a parallel plate capacitor like the one we could be having here. What do you realize from the expression? I want you to realize and discover what happens if you increase this area of contact, this area, if you increase it. And maybe now it was that one, but now we are increasing the area. Now our plate capacitors are like this one. What happens? Because you have increased the area, it means the capacitance will do what? Will increase. Okay? What happens when you increase the distance? For instance, we have this distance D from here to there. We can increase it. We can increase it. Okay? We can increase it and you can see now the distance has become bigger. So what happens to the capacitance of such a capacitor plate? You have increased the denominator. Therefore, we should be expecting the value of the capacitance to do what? To reduce. We have another parameter, epsilon. Yeah, here is epsilon naught and is constant. But we can change the medium in which this thing is being done. Therefore, by changing the permittivity. So what happens if we increase this? If you increase this, then the capacitance will increase because it is a numerator. That one is taking us back to what we studied before. That if you bring a dielectric, any material that is a poor conductor, if you bring a dielectric and you press it between these capacitor plates, the capacitance will do what? Will increase. Why? Because you have increased the permittivity. I know you have got a point. Please continue and don't leave this channel. Please continue inviting all your colleagues to come so that we can study together. That is at Back Science Education Consultants, BSc. Everything to do is understanding. Actually, we are available and we are providing all that you need for your performance. So therefore, the capacitance of a parallel plate capacitor is given by A epsilon naught over D. That is when it is in vacuum or when it is in air. But you can now press something, as I've said. You press now this one, which is a dielectric, which has a different permittivity, which is not epsilon naught, which is epsilon. So therefore, the capacitance will now become A epsilon out of D. And of course, this epsilon can also vary from material to material. And the way we compare which materials have more permittivity than others is by comparing the capacitance, if that material is pressed in this space, to the capacitance when the space is filled with air for different materials. Then you can know that this one is better, this one is like this one can help us to this extent. And therefore, the measure of that, we compare the capacitance when we have inserted that material there and the capacitance when the material is not there. That measure gives us what you call the relative permittivity of the medium. Therefore, the relative permittivity of this medium that I'm inserting here is the ratio of the capacitance of this capacitor. Okay? Is the ratio of capacitance of this capacitor when this material is there. to the capacitance of the same capacitor when this one is not there, as long as you keep area constant and the distance of separation of the plates constant. That one is termed as a relative permittivity. Oh, yes, relative permittivity. We have said this is the capacitance when I have put this material. Okay? To the capacitance when there is air or vacuum. To the capacitance when there is air or vacuum. You realize that this A will cancel, this D will cancel, and then our relative permittivity will remain epsilon out of epsilon naught. And therefore, some people can also define relative permittivity as the permittivity of the medium. Excuse me. So therefore, we can take note of what we have discussed, because I know it will be better. So I'm saying that consider a parallel plate capacitor whose metric strips are each of area m squared. Is there? You can write, consider parallel plate capacitor whose metric strips, this one, are of area m squared and are at a separation d as shown above or as shown there. If 2 is the magnitude of charge, if 2 is the magnitude of charge on either capacitor plates, this and this, then the electric field intensity E of the field between the capacitor plates is given by E equals sigma over epsilon naught, where sigma is the charge out of area, because sigma is the surface charge density, where sigma the surface charge density equals that. Full stop. So E becomes that. This means that E becomes the Q of A naught. You can maybe call it equation 1. Also, E is equivalent to potential gradient, which is equal to V out of D. So E is V out of D. That's equation 2. So from 1 and 2, we have the charge out of A epsilon naught equals V out of D. So when I cross multiply this on this side and divide this on this side, where we shall have 2 out of V equals A epsilon naught out of D. But 2 out of V is the capacitance. Therefore, capacitance equals A epsilon naught out of D. This is a very important statement, where epsilon naught is the permittivity of free space. If a dielectric of permittivity epsilon, if the dielectric of permittivity epsilon is between the capacitor plates, then the capacitance becomes A epsilon of D. Then the capacitance becomes A epsilon out of D. Note, relative permittivity of a medium, in brackets dielectric, cross bracket, between the capacitor plates epsilon r equals permittivity of the medium, in brackets when the dielectric is between the capacitor plates, then divided by permittivity of free space. You can say when air or vacuum is between the capacitor plates. When air or vacuum is between the capacitor plates. Therefore, epsilon r equals epsilon out of epsilon naught. And of course, in future, if we need this one and we have this and this, then you can see that the epsilon will be equaling to epsilon r times epsilon naught. We shall also use this one at some point in the near future. And definition. Dielectric constant or what you call relative permittivity. Dielectric constant or what you call relative permittivity is the ratio of capacitance of a capacitor, is the ratio of the capacitance of the capacitor fed with the dielectric to the capacitance of the same capacitor when fed with air or vacuum. The ratio of capacitance of a capacitor fed with the dielectric to the capacitance of the same capacitor fed with air or vacuum. You can always find such important statements at Back Science Education Consultants. Trust me, they are only found there. You just need to invite a colleague so that you learn together. You come together, then you achieve. I want us to do a calculation so that we see the applications of some of the things that we have studied. We shall just do one for this particular lesson. We are just doing one calculation. Yes, so our question is this: that two horizontal parallel plates of area 500 centimeters squared are mounted 2 millimeters apart in vacuum. The lower plate is asked and the upper plate is given a charge of 0.05 microcoulombs. That neglecting edge effects, find the electric field intensity between the plates. They calculate the electric potential on the upper plate and the capacitance of the plates. We are just given a very simple task that we can maybe do some sketching, that they are two horizontal parallel, just like we had them here, this and this, okay? They are both horizontal. You know, these plates can be changed. Maybe they can be like this, they can be like this, they are still parallel, but these ones are horizontal and are parallel, okay? Yes, so they are like that. So this is the upper one, this is the lower one. We are told that they have an area of 500 centimeters squared each. So the area is 500 centimeters squared. Of course, we shall change meters squared. You know what we do. Then the distance of separation is 2 millimeters. We shall also change it to meters when we are performing when we are doing the calculation. Excuse me. And then we want to find electric field intensity between the two plates. So maybe we can do some sketching and we show this is just one plate here. Okay, this is the upper one, then there is the lower one. We are told the area is there, the distance is given here. So this one is given a charge, and this one is earth, meaning that one creates that kind of a potential difference V that will be across. We are finding the electric field intensity. So what is electric field intensity? Okay, we have from this lesson we have known that, maybe I can remove this. We have known that electric field intensity is this one, the sigma out of epsilon naught, which is also the charge out of a epsilon naught. Okay, the value of epsilon naught is always a constant. It can be provided, and the charge is given. We are told the charge is this. So therefore, our electric field intensity will become 0.05. It is micro exponent -6. Then the area from centimeter squared to meter squared is exponent -4. Then times the value for the epsilon naught should be now 8.89 exponent -4. And when you perform the mathematics so well, you are supposed to get a figure close to 1.125 exponent 5. 1.125 exponent 5 volt per meter. That is the value of electric field intensity. We need electric potential. Electric potential. When we have field intensity and D, we know that E is the potential gradient. So we have E and D, meaning V is E times D. Therefore, our V will be E then times D, and the E is given here 1.125 exponent 5. Then the distance of separation is 2 millimeters. So when you are changing from millimeters to meters, is exponent -4. And when you perform the calculation, you should get a figure close to 2.25 exponent 2.25 exponent 2. That is volts. Okay, you press your calculator and compare. And lastly, we want the capacitance. Lastly, we want the capacitance of the capacitor. What is the value of the capacitance of the capacitor? How do we get the capacitance? It has very many forms. But from the original definition, we say that capacitance is 2 out of 3. And you can see the charge we have it, and the voltage we have also got it. So you can substitute. So this is 0.05 exponent -6, then out of 2.25 exponent 2. And what do we get when we substitute there? Press your calculator. I can retrieve the figure that I have here, which is 2.2125 exponent -10, or something close to that. 2.2125 exponent -10. The unit of capacitance, a farad. So that is that. Okay. Yes. We also had all studied that the capacitance is A epsilon up to T. I want you to use this one. Use that and see whether you will be able to obtain the same value of the capacitance. That is Teacher Course. Don't forget to subscribe to our YouTube channel at Back Science Education Consultants. Please be there. You are always highly welcome. Thank you for following our lessons. May God bless you. May you be blessed. May God bless you.